Hello. Hello and welcome to this read through of vectors. We had covered till last split. It will probably take two more videos or three, most probably two. So I'll try to finish this in two videos. So let's continue. So the next function which we are looking at the methods of vectors is rsplit, takes operates on a vector and takes a predicate which is a mutable closure returning a boolean, and it returns an RSP. That is, we'll see what it returns. It returns an iterator over subslices separated by elements that match predicate, starting at the end of the slice and working backwards. The matched element is not contained in the subslices. So here our predicate is that the number is equal to 0. So if you look from the right side, then 44 and 55 are there before 0. So they will be in the first slice. Then 0 will not be in any slice. Then we have 32, 22, and 11. Okay. So we have that. And after that, it will be none. As with the split, if the first or last element is matched, an empty slice will be the first or last item returned by the iterator. So here you see that from the R split side, it is the end. At the end, we have 0, and predicate is that it should be an even number. So the first number is also matching the predicate because it is even. So the first slice will be empty as well as the last slice will be empty. And in between we have 3, 5 and 1, 1. Okay. Then we have our split and split. Similar behavior, except that the split will be equal to the iterator which will return the slices will be mutable. So for example, you can look at here, you take the group and group 0 is assigned count. So count starts from 0 and then it is increasing by 1. And our predicate is that it should be divisible by 3. So 500 is here, so it becomes 1. And then 200, so it becomes 2. And then 100, it becomes 3. So that's how the predicate works. Okay. Because there are how many items are divisible by 3 here. So count starts from 0. Then if you look at 500, then it is the first slice is 500. Okay. So 500 will become 1. And then 300 is the second one. So 200 becomes 2. That is the second group. That will come here. And then in the next one, 300, after 300 will become 3. So third group will be 100 and 200, 100 and 400. So there are three groups, 500, 200, 100, 400. But in this one, this is the 0th element in this slice. So it becomes 3. Now we have splitten, which takes a number of type usize and a mutable function, mutable closure returning boolean. Returns an iterator over subclasses separated by elements that match predicate limited to a returning at most n items. The matched element is not contained in the subslices. The last element returned, if any, will contain the remainder of the subslices. Note that here uh, the slice which is being returned by a split mute, that is group, is actually part of the vector. That is why this changed the original vector. So keep that in mind. Okay. Now we were reading this. The last element returned, if any, will contain the remainder of the slices. Example. So we have this slice. Okay. So if you look at this, then 3 and 60 are the items where number is divisible by 3. So at most items is at most returning at most 2 items. So it will return 10 and 20, and since it has to return 22 items at most, it will put all this into the second item. So it will become 20, 60, 50. Then we have split and mute, similar to split, but this time the return groups will be mutable. So here the first group will be 10, 40, and we are setting the first elements to 1. So 10 becomes 1, and then 20, 60, 50 is the second group. So 20 becomes 1 here. Now R split n is there, similar but from the right side. R split n unit is similar from the right side. Split ones we don't care about nightly API, then there is contains. So it requires a trait to be satisfied, that is partial equality trait is to be satisfied by the type, which is the type of the vector. So here it is integers. So integers do satisfy partial equality trait. Returns true if the slice contains an element with the given value. Let me see if voice is being recorded. Yeah. Okay, this operation is on because it has to traverse the entire array. Note that if you have a sorted slice, binary search may be faster because binary search will give us log n. So here our vector is 10, 40, 30. You are looking for 30, it will be found. And note that it takes a reference of this type. So you have to send the reference of 30. So 30 will be found in this. Now why it takes reference is because the elements of vectors could be quite large. Okay? Each individual element could be quite large. So a reference is taken. If you do not have ampersand t but some other value that you can compare with them, for example, string implements partial equal str, we can use iter.any. So for example, we create a string from hello and we take world and then we iterate over, create an iterator also from vector and we take any on that and each element is compared with hello and hi. Okay. So that is another way of doing it. Then we have start full. Returns true if the needle is a prefix of a slice or equal to the slice. So it operates on a vector, takes a needle or a reference which of type t, which is the same as type of vector element. So 10, 40, 30. It starts with 10, which is 2. Start with 10, 40, true. Start with the equal value as vector, true. And then it does not start with 50, does not start with 10, 50. Always returns true if needle is an empty slice. So if you compare with the empty stuff, then it will always return true. Now we have ends with similar to start with, but it will look at the end side of the vector. So 30 here, 40, 30, we all will return true. 50 and 50, 30 will return false. Here empty slices will return true as well. Strip prefix. So takes operates on a vector, takes a prefix p. So p is a slice pattern and its side type, and t is the return type t must satisfy partial equality. So the type of vector should satisfy the partial equality. Returns a subslice with the prefix removed. If the slice starts with prefix, returns a subslice after the prefix wrapped in sum. If prefix is empty, simply return the original slice. If prefix is equal to the original slice, returns an empty slice. If the slice does not start with prefix, it returns none. So for example, here we have 10, 40, 30, and we are checking whether it starts with 10. Then we return sum 40, 30 for the entire range. Okay. Then we check for 10, 40, then it will return 30. If we give the entire slice, then it will return an empty slice. If we give 50 or 1050, it will return none. Similarly, say prefix is he, and we are looking at hello, and that is a byte type, hello.strip prefix, prefix as bytes, then it will return LLO bytes as ref. Then we have strip suffix similar to prefix but operates on the right side of the slice. Then we have binary search. So binary search implements the standard binary search. Binary search is this slice for a given element. If the slice is not sorted, the return result is unspecified and meaningless. If the value is found, then result OK is returned containing the index of the matching element. If there are multiple matches, then any one of the matches could be returned. If index is chosen deterministically, but is subject to the index is chosen deterministically, but is subject to change in future versions of Rust. If the value is not found, then result error is returned containing the index where a matching element could be inserted while maintaining sorted order. C also, we'll see all these. So example says looks up a series of four elements. The first is found with a uniquely determined position. The second and third are not found. The fourth could match any position in 1 to 4. So we have this vector and we are looking for 13. The 13 is found here. So the index is 9 and OK 9 is returned. 4 is not there, so it will return at position 7. So at position 7, if you see 1, 2, 3, 4, 5, 6, 7. So here, since it will be 0 index, so at this position, we can insert 4. Then we have 100, which can be inserted here. So it returns 13 and so on. If you want to find the whole range of matching items rather than arbitrary matching one, that can be done using partition point. So I think we will look at partition point and it will be there. Partition point, it is part of primitive slice. Okay, let's go and read that. Okay, so it operates on a slice. What it does is it operates on self with a predicate, and predicate is a mutable closure. Returns the index of the partition point according to the given predicate, the index of the first element of the second partition. The slice is assumed to be partitioned according to the given predicate. That means that all elements for which the predicate returns true are at the start of the slice, and all elements for which the predicate returns false are at the end. For example, 7, 15, 3, 5, 4, 12, 6 is partitioned under the predicate x percentage 2 is not equal to 0. All odd numbers are at start, all even at the end. So that's what we are doing here. So here our predicate is x is less than 1. So 0 is at the beginning and everything else is on the right side. So low will be 1 here. Okay. And partition point again, high is x less than equal to ampersand 1. So high will start from, there will be 5 high. So less than equal 1, 2, 3, 4, 5. So count is 5 now. So high will contain 5 points. Now binary search, we operate on low and high, and we check whether it contains the R. Okay, R is not given here. Now we look at, we iterate over the low side of the slice, and we see that everything is less than equal to 1. We iterate on the high side between low and high. We see that everything is equal to 1, and we iterate after high side. We see that everything is greater than 1. So partition point is that we check if x is less than 11, then number of items is 9, and if it is equal to 11, then also item is equal to 9. So if we do binary search 11, we see that 11 is not there and we return error. Okay, the range of equal items is empty. So that's what you have to figure out from this. So you see the range of these two are same. That means 11 is not present. If you want to insert an item in a sorted vector while maintaining sort order, consider using partition point. So we want to insert 42 in this. So we check for all the items which are less than equal to 42, and it will give us the index over here, and we put that insert item on that index, that number. Okay, so it will become 42. Then we have binary search by, so it will take a predicate. Okay, and accordingly it will search based on binary search algorithm. Binary search is this slice with the comparator function. The comparator function, that is this closure, should return an order code that indicates whether its argument is less, equal, or greater than the desired target. If the slice is not sorted, or if the comparator function does not implement an order consistent with sort order of the underlying slice, the return result is unspecified and meaningless. If the value is found, then result OK is returned containing the index of the matching element. If there are multiple matches, then any one of the matches could be returned. The index is chosen deterministically, but is subject to 10. So it's the same stuff we have. So we look up a series of 4 elements. The first is found and is included in the same example we have. So we look for 30 and we invoke the comparator function on probe. Okay, probe is the element which will come and will compare, and we see that it will be found here. 13 will be found at location 9. And then we compare 4 with the elements, and we see that it is not found. But position 7 will be appropriate position. And then we look at 100 is not found, position is 13. That's how it works. Then we have binary search by key. Here it will take 3 arguments. It will operate on the vector. It operates on a type D, a value of type D, reference of type D, and a closure where the function the closure returns the element of type D, which implements the OR trait. Binary searches the slice with the key extraction function, assumes that the slice is sorted by the key. For instance, we'll sort by key using the same key extraction function. If the slice is not sorted by key, the return result is unspecified and meaningless. So this is all the same. So here we have this vector and we are looking for 13. Okay. So it takes 13 and it also takes the mutable function. Okay. So 13 is your D. Okay. And it looks at AB and returns B. So here this will match. Okay. So if you look at this position 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 means at this position if you insert 13, or rather it is found at that position 13. If you try to find position 4, it is found at position, it is not found. The second key is not there anywhere. But you can insert this at this position here after 2, 3. Okay. So that is position 7, 0, 1, 2, 3, 4, 5, 6, and 7. And similarly for 100, it can be inserted at the end. Then we have sort unstable, which takes mutable self and it should be bound by the trait, or sort the slice in ascending order without preserving the initial order of equal elements. This sort is unstable, that is, may reorder equal elements in place, that is, does not allocate an order n log n worst case. If the implementation of odd for t does not implement a total order, the function may panic even if the function exits normally. The resulting order of elements in the slice is unspecified. See also the note on panicking below. For example, a closure which takes 2 arguments a minus b dot compare with a is a comparison function that is neither transitive nor reflexive nor total. A less than b less than c less than a, with a is equal to 1, b is equal to 2, c is equal to 3. But C is not really equal to 3. C is 3 and A is 1. So 3 is not less than 1. For more information and examples, see the OR documentation. All original elements will remain in the slice and any possible modification via integer mutability are observed in the input. Same is true if the implementation of OR for T panics. Sorting types that only implement partial OR such as F32 and F64 require additional precautions. For example, F32 nan is not equal to F32 nan. It does not fulfill the reflexivity requirement of OR. By using an alternative comparison function with slice colon sort a stable unstable by, such as F32 total CMP or F64 total CMP that defines a total order, users can sort slices containing floating point values. Alternatively, if all values in the slice are guaranteed to be in the subset for which partial order partial comparison forms a total order, it is possible to sort the slice with sort unstable by AB A dot partial CMP B dot on that. Current implementation. The current implementation is based on IPN sort by Lucas Bergdahl and Orson Peters, which combines the fast average case of quicksort and the fast worst case of sort, achieving linear time on fully sorted and reversed inputs. On inputs with k distinct elements, the expected time to sort the data is O times n into log k. It is typically faster than stable sorting, except in a few special cases where the slice is partially sorted. May panic if the implementation of odd 40 does not implement the total order, or if the odd implementation panics. If, for example, we have a vector v 4 minus 5 1 minus c2, and we perform sort unstable, then it will be sorted 2 minus 4 minus 3 1 2 4. So I think let me see how much remains. Okay. Okay, we will complete this one. Next one, we will look at this sort unstable by key. So it takes a closure here, which returns a key k, and k should support the total ordering stuff. Sort the slice in ascending order with the key extraction function without preserving the initial order of equal elements. So this is the same information here. Okay, current implementation information is same. Panic is the same. So here we are sorting on the basis of absolute value. Okay, that is our closure. Okay, and if we sort by absolute value, then it will become 1 2 minus 3 4 minus 5. So I'll stop here, and in the next video we will start at select another unstable. Okay, and we should be able to finish this in the next video. Let me see a bit. It is a bit, may take 2 more videos. There is still quite a bit of information there. So we will take probably 2 more videos to finish this. So I hope that you are enjoying this read through and learning a lot about vectors in Rust. So I thank you for watching the video, and we'll meet again after 4 days with another video on Rust. So once again, thanks a lot for watching the video. Stay curious, have a nice day, and enjoy.